Hey guys, welcome to the the fifth video that we've done, the sixth video, I guess, on physics. In this one, we're going to continue our conversation about uniform motion. Last video was all about how we can analyze something in uniform motion, what we say quantitatively, like using a formula to understand how its distance and time and speed are related. Today we're going to talk about how we do the same thing except with graphs. And what I like about this section is that it really goes well with what you're taking in math right now on linear equations, because what we're going to be looking at is a linear equation for something that's moving. So it's nice that we're doing these two units at the same time, because there's going to be a lot of overlap between what we talk about today and what you guys talk about in math class. All right. My understanding is that Mr. Brony hasn't quite covered up to the stuff I'm about to say today, which is totally fine. We do get to it faster than they do. So I'm going to do a bit more explanation than I normally would, but hopefully by the time you're done your math unit and this unit, graphing makes a ton of sense to you. Graphing is really important in science. It doesn't matter if you want to go into physics, chemistry, bio, or just science 20. You need to be able to read a graph. You need to be able to realize what that graph is telling you and analyze the different parts of it to say what's happening in the different parts. All right. So just some brief things about graphing before we even get any further. Number one, we have our x on a graph. We have two axes typically. We have our x-axis and our y-axis. I know you guys know that from math class. X is our horizontal one, y is our vertical one. And we'll talk all the time about how x is typically our independent variable and y is our dependent variable. What we mean by that is y, whatever happens to y, responds to what x is doing. X is changing on its own, and y will get bigger or smaller or change in some way based on what x is doing. All right. In science, we talk about these a lot as our manipulated variable and our responding variable, meaning that this is the one that we're changing in our experiment, and then we look to see what our responding variable does as a response to how the x variable is changing. Now, when we graph stuff in physics, when we're talking about speed, in particular in uniform motion, typically we're talking about two units, two variables that come together to create speed. Remember that speed is based on the fact that we have a distance that we've traveled and a certain amount of time that we traveled for. So what we have to do is figure out which of those is our dependent variable and which one is independent, which one is changing on its own, and then which one is changing as a response to the first one. Okay, so our two units, we have distance and we have time. If you think about something traveling, what you want to think of here is which one of these causes the other one to increase, or which one of these causes the other one to change. And the way you can think about that is as follows. All right. In our first case, let's say that we think distance is our independent variable. What we're saying is that as distance increases, time moves forward. All right. In other words, the longer I travel for, the more time passes, which is not necessarily true because it depends how fast I'm traveling. Right. Or when we think about it the other way, the longer I travel for, the further I go. That is true. It doesn't matter what speed I'm at. If I'm going 20 kilometers an hour or 50 kilometers an hour, if I'm traveling for more time, I'm going to cover more distance. So what that means is distance is changing in response to time. So what that tells us is that our independent variable, our x variable, is going to be time. And we could measure that in hours or seconds. Okay. And then our responding variable is going to be distance, which I can measure in meters or kilometers. It doesn't really matter. Okay, it depends on what the scenario is that we're given. So as we go forward, every distance time graph we're going to make is going to have this setup. Time is always going to go down here. Distance is going to go down here because as time increases, the distance I travel increases. All right, so that's why it's our dependent and independent variables. Now, as we head forward, a couple big things. Number one is you need to have already started on your booklet at this point. Normally when I teach this section, we do it as a large class discussion where we have small bits that we talk about, followed by you guys working on some things, followed by talking, followed by working. It's a little bit weird to do that online, so I tried to split it up a little bit between stuff you should do in the booklet and then stuff you should do in this video. So at this point, if you have not done the graphs on page 5 and 6 of your booklet, you need to stop now, okay? Go to page 5 and 6. You will see some data on 3 separate data tables and then 3 little bits of kind of graph paper. I want you guys to graph the data with a line graph, okay? And do that now before you go further in the video. The video assumes that you have made those 3 graphs, all right? It also asks you to do slope calculations. Don't worry about that until after. I will go through the slope calculations with you as a part of this video. Seriously, if you have not done those graphs, stop watching. This is your last warning. I will track you down. Okay, so now that you have your 3 graphs, if you look at them side by side, which I know is a little tough to do because the one's on a different page, you should have the 3 graphs that look something like what I have here, except for you, they'll all be a separate graph. I drew all 3 lines on one. All right. Before we go further, the one thing I want you to note is that based on just the table of values that you were given, these objects are definitely in uniform motion. And the way that we know that is they are covering the same amount of distance every second. Now I screwed up a little bit. I forgot that in your notes this is in centimeters, not meters, but it doesn't really change what's happening here. Okay, so we know just from our table of values that that slow one is going 1.4 centimeters every second, right? Because it always goes up by 1.4 centimeters. The medium one is covering a little bit more ground. It's going 2.1 centimeters every second. And our fast one ends up going 3 centimeters every second, all right? So we can tell just from the table of values that this one's going to be the fastest, this one's the slowest. But what we want you to do now is look at this graph and start to figure out what it is about this graph that tells us that the object is traveling in uniform motion, all right? So you'll see on page 6 of your notes, there's a question that says, what property of the shape of the line, the shape that these lines make, tells us that they're traveling in uniform motion? And hopefully what you guys notice is that every single one of these lines is straight, all right? If those lines curve at all or change directions, like if one of them went up and then down like this or curved like this, okay, that means it's not moving in uniform motion. But we can tell from the graph, without, if I didn't even give you the numbers, but if I just showed you these pictures and I asked you, are these things in uniform motion? The way you can tell that they are is that they form a straight line. Okay, so that question on page 6 that says what property of the shape of the line tells us that the object's traveling in uniform motion, it's that it's a straight line. Okay, even if I had a flat line, like even if I had a line like this guy here, just quickly sketch one out. Even if I had that thing is still in uniform motion because it makes a straight line. It's just not moving. That's all. That's the idea of a flat line like that. But it is still in uniform motion. All right. The next question says, what property of the shape of the line tells us that the object is moving faster? As in, what is it about this line that tells me it's faster than this one and this one? And how do I know that my yellow line here, my medium one, is faster than the slow one, other than the fact that I put the labels on them? The biggest thing really is that this one, this red line, this fast one, is steeper. That's it. Okay, so if the steeper the line is, the faster the object is moving. And the reason is, if I just change colors really quick, if I look at, let's say that this here is this time interval here, these 2 lines I just drew, let's say that's 1 second. All right, so the distance between this weird green line and that one, let's say that's 1 full second. Right, in that 1 second, this red line, okay, like in this distance here, that red line went this far. Okay, it covered this much distance here, which is fairly big. In that same time difference, right, in that same second, this blue line here covered way less distance. Okay, it only went up about this much, whereas this red line covered this much. So the red line covered more distance in that 1 second, which makes the line steeper. So when it says what property of the shape of the line tells us that the object is traveling faster, the steeper the line is, the faster it's moving. And then what property of the shape of the line tells us the object is moving slower? How gradual it is. The fact that this blue line here is not nearly as steep as the red line, okay? So the more shallow something is, the more gradual it is, the slower it's going. The steeper it is, the faster it's going. Okay, so I'm just get all that mess out of there. So the big thing I want you to understand from this picture and from those 3 graphs that you made is 2 important properties. If I just gave you a graph with no numbers on it whatsoever, you should still be able to tell me if something is in uniform motion or not based on whether the line is straight or not. And then you should, if I gave you 2 lines on a graph, you should be able to tell me if something is moving faster or slower than the other one. And we do that by how steep the line is, all right? We can also, the only other thing you could tell me really is if something is moving or not. And again, didn't even draw that very well. The way you can tell is whether or not it has a straight line, okay? So if I have something like this, there we go, that would be an object not moving. Those are the 3 kind of bits of information that you should be able to tell me just from looking at a graph. All right, so let's talk a bit about what other things we can learn from the graph that are less qualitative. Everything I just told you, you can just look at the picture and say, oh, well, it's a straight line, it's uniform motion. Oh, it's steeper than the other one, it's moving faster than the other one. That's all qualitative stuff. But we want to be able to get some quantitative, some numbers-based information from our graph as well. All right. So if you look at page 6 of your notes, where it actually says notes there, and there's a bunch of blanks to fill in, that's in the PowerPoint that I want you to look at after this video. Okay. But I'm going to kind of go through some of the things it talks about, because there's 2 kind of measurements that we can get from a graph that can give us different bits of data depending on what we're looking at. So if I give you a graph and I ask you to tell me how far it's gone at a certain time, you should be able to do that. If I ask you to tell me how fast it's moving in numbers, you should be able to do that as well, all right? So let's talk about how we do both of those things. So number 1, when we look at a graph, we can, a lot of times I'll say, okay, at 4 seconds, how far has this thing gone, all right? We say that at that point, we're looking for the y value or the value of the line graph. It's a really easy thing to do. There's not a ton of work to do here. All we have to do is say, okay, at 4 seconds, how far has it gone? And all I'm going to do is look at my 4-second mark here. Ooh, that line's a little thinner than I like. Okay, look at my 4-second mark here. Okay, and that's where my dot is, or wherever it hits on the line. It doesn't even need to be a dot. And then I can say how far has it gone. All I have to do then is read what the y value is. So this thing has gone at 4 seconds about 10 meters. If I were to do it again at, let's say, 7 seconds, right in between these guys, I can still do that. So how far has it gone at 7 seconds? It's kind of right in between those guys. So I'd say it's gone about 17.5 meters. That is a bit of an estimate on my part, and I didn't use grid lines here, so it's a little bit harder to tell. If I'd use grid lines, this would be a lot easier, okay? So the big thing to understand here is actually quite simple. So what we're trying to do here is just say, where is the y value at that given time? So at like 5 seconds, what is the y value here? And we just have to go up from where our time is over to where it is. So what I'm saying is if I gave you a graph like this and I say, hey, how far has that thing gone at time 9 seconds or whatever, you need to be able to tell me how far it's gone. So to find distance from a distance time graph, we just look at the y value of our line at that particular point. So the next type of question I can ask about this is a lot trickier. The next question I can ask is, what is the speed of the object during this trip? Okay, and this one's not so obvious because I don't have on either axis the speed, but I can figure it out by looking at my line and determining what we call the slope. Okay, remember what we said, that how steep the line is tells us how fast it's moving? It turns out that we have a measurement for slope, or for steepness, which is the slope. Okay, so the slope of a line tells us how steep it is, and it turns out that in physics, the slope of the line happens to tell me the speed that we're traveling. Okay, and the slope is a little bit complex to figure out. All right, so what the slope is basically how, as I said, it's how steep the line is, and what that really tells us is how quickly the responding variable is changing for every one change of my time. In other words, how much is my distance changing every 1 second, which is what speed is, right? We measure it in like meters per second, kilometers per hour. Okay, and it's always a 1 next to that second or hour. So basically just what is my distance changing for each time my time increases. It's kind of a weird sentence. In other words, it's the rate of change. And you learn all about that in math as well. All right. So the slope, the steepness of the line tells us how fast it's moving. To determine the speed, to determine the slope from a graph, because I don't just have v equals d over t to use anymore because I have so many different points I could use. All right. So what we want to do to determine slope is pick any 2 points along the graph. It does not, if the line is straight, it does not matter which 2 points you use. I could pick this point and this point, this one and this one. It does not matter. But for the sake of this example, I'm going to pick 2 points here. I'm going to pick this one and this one. I chose those pretty arbitrarily. I actually don't care which ones I chose. I'm just trying to show you it doesn't matter what you do. Now, what we have to do is label these points based on what their coordinates are, just like we would do in math, all right? This point here, this first one, we're going to call x1, y1, okay? This point here, I'm going to call x2, y2, right? The reason I gave them those numbers is that this one occurs first, going from left to right. So the way you figure out which number is x1 and y1 is which one happens first as we go this way. So this one here is going to be my x1, y1 value because it has the smaller x value. This one here is going to be my x2, y2 because it has the bigger x value. We care about the x's, we don't care about the y's. So if I had a line that, you know, went like this, which we will eventually have, this, and I had like a point here and a point here, this would still be x1, y1. This would still be x2, 2y2, just because its x value here is less than this one. All right, let me get rid of that junk that I just drew there. Perfect. So now what we want to do is actually put the actual coordinates that these guys have. So x1, y1 here, the x value it has is 2, and the y value it has is 5. Okay, this one over here, the reason I got those is, again, x is this is 5. Okay, we're going to do the same thing with our x2, y2 value. My x value on this one is 8. Oh, wrong tool. Value here is, oh, geez. Oh, my goodness, I'm falling apart here, guys. The x value here is going to be 8. The y value here is going to be 20. Okay, and again, that's just me reading what the coordinates are. All right, we're going to come back to this. I just want to start with a blank graph a little bit, just so that we have a little more room to draw things. Okay, I just wanted to zoom out a bit there, just so we had some more room to do our math with. All right, so we've already picked our 2 points, and again, it could have been any 2 points. I don't care. All right, but I chose these two. And the way we determine slope is the following formula, and it's got a couple names. Typically what you'll see, especially in math, they love this term, is that when we do the slope, what we're looking at is how much do we rise, how much does our line go up on the y value over the run, all right? You'll hear in math all the time, slope is calculated by going rise over run. In other words, we're looking at how much our y value changes, because that's how much we rise, over how much our x value changes, because that's how much we run along this way. The actual formula, and this is in your data booklet, it's on, I believe, the same page as the other physics formulas, is going to be y2 minus y1 over x2 minus x1. In other words, what we're doing is going the difference in our y values, basically how big that gap is that I just drew, divided by the difference in our x values, basically that there. I just didn't want to cross out my numbers, but it really should be going, connecting that little triangle that we've got, okay? Now we've already identified y2, right? We said that y2 is going to be 20. We said that y1 is going to be 5. So we're going to go, in terms of the math that we're doing, we're going to go 20 minus 5, okay? y2 minus y1. But if I should just back up a little bit here, remember that our y values are telling us our distance, which in this case on this graph is measuring meters, okay? So I'm really going 20 meters minus 5 meters. Okay, and those will be important for us. For the x values, again, I'm looking at x2, which is 8, minus x1, which is 2. So I'm going to go divided by 8. And remember, time is in seconds in this case. So I'm going to go divided by 8 seconds minus 2 seconds. When I plug those numbers in, I'm going to get 15 meters divided by 6 seconds. Okay, and this is why I wanted to show you guys the units. Remember I said that the slope tells us the speed? Look at this. I'm using meters per second. That is speed, right? I'm going meters over seconds. I still need to do this math though. And when I go 15 divided by 6, what I'm going to get is 2.5 meters per second. Okay, that's going to be my final answer. Normally, I would say, hey, make sure you do have the right significant digits here. And technically, with the way that I wrote this down, I should only have one significant digit. But this is a really quickly, poorly made graph. Really, I should be going 2.0, 4.0, 6.0. So I'm just going to leave it at this for now. It's just for my demo that I'm doing for you guys. All right, I want to do one of the examples, or one of the slope calculations that you guys have to do. So if you look at page 5 of your book, I want to do the slope for the slow graph, okay? Now, to do the slope from the graph that you guys made, it's actually easier than the one I just showed you because I'm giving you the table of values. And I'm only going to focus on 2 points from it, and it does not matter, again, which 2 points I chose, all right? But I'm going to look at the time at 5 seconds, where it says we've gone 7 centimeters. And I'm going to look at the time at 10 seconds, and 14 centimeters. But again, you can pick any 2 points. You could have picked 6 seconds and 1 second. You could have picked 9 seconds and 0 seconds. It does not matter. This is still your table. You just pick any 2 points on the line. From there, we have to figure out which one of these is x1, y1, and which one is x2, y2. That's really easy to do. Whatever one has our smallest x value, our smallest time, that's going to be x1, y1. Okay, so here's my x1, y1, here's my x2, y2. So to figure out the slope for this, we're going to use that same formula, y2 minus y1 over x2 minus x1, okay? When I plug that into my calculator, I'm going to take these numbers straight out of my table of values and match them up to where they belong, okay? So y2 is my 14 centimeters, so I'm going to go 14.0 centimeters minus y1, which is 7 centimeters, divided by my x2, which is 10.0 seconds, minus my x1, which is 5.0 seconds. Okay, and when I plug that into my calculator, what I'm going to get is 7.0 centimeters divided by 5.0 seconds. And when I do that math, I get about 1.4 centimeters per second. Okay, this time I do have the right number of significant digits because when I built this table, I wanted to make sure we had the right number. All right. You guys should be able to now do the slope calculation for the medium and the fast one. You follow the same process. Pick any 2 points in your table of values, figure out which one's x1, y1, which one's x2, y2, and then plug those numbers into your formula. Okay. So those guys that we just did, that's nice when I give you a table of values, or it's nice to be able to figure out the slope if the line starts at 0, which every single one we've looked at has done. Every single graph we've looked at, I made sure that we started at 0 and we went like that, okay? Or like that, or whatever, it doesn't matter, but we always started at 0, okay? That's not always the case, and we can get really screwed up if we don't start at 0, all right? So what I want to show you guys is how you can figure out the slope if you're given a graph like this one here where we don't have a table of values and we don't start at the origin. We don't start at 0, 0. We can still find the slope of this. What we have to do is still pick any 2 points on the line. But we have to be careful to make sure we use what I call good points, ones that are a little bit more accurate, a little bit easier for us to figure out. What I'm saying, in other words, is pick points on the line here where the line intersects with both sets of grid lines. In other words, you want it to hit corners like this here. So we're looking for spots on the line where it hits the intersection between the X and Y grid lines. So when I go down this line, I'm looking for good points that I want to use that go through those intersections. There's one right here, okay? So I'm going to just circle that. That's going to be a really nice point for me to use. Oh, geez, that's a terrible circle. Try that again. Right there, okay? And then there's another one actually right at the very beginning, okay? Because these guys don't quite go through perfectly. It doesn't quite hit that intersection here, but we hit it right here, okay? So this is going to be a good point for us to use as well, right? So when I plug these into my slope calculation, this one here is going to be my x1, y1. This one here is going to be my x2, y2, okay? I don't worry so much about the fact that the line is going down. We'll talk about that more next week. But basically, we would do the exact same thing here. I would put in I put in 10, because that's my y value here, minus 25, divided by 4, minus 0. So I go 25 divided by 4. All right, don't worry so much about that. If you do the boot camp that I posted, it should help you out a bit. Okay, we'll talk more about these lines that go down next week. We'll see this a lot more. Okay, it turns out we can do more than just graph our distance and time. The second type of graphs that we look at in physics are what we call speed time graphs. And hopefully you guys had a second, as I said in the instructions, to graph the speed time graph on page 7 of your not your data booklet, your regular booklet. So again, on page 7, I provided you with a table of values and just wanted you to graph it. This one is super easy to graph. All right, because the speed, if you look, is the same every second. What these speed graphs do is just tell us how much something is speeding up or slowing down and how quickly it's doing that. With this one, we notice that the speed doesn't change. It's why it's such an easy graph to make. This particular object is traveling at 3.5 centimeters every second. So it says on page 7, is this object traveling in uniform motion, and how can you tell? This object is definitely traveling in uniform motion because its speed is not changing. But then the second question, if you've made your graph, you should have basically this right here. My dots are a little up and down because it's hard to draw this. But the second question says, what is it about the shape of the line that tells you that this thing is in uniform motion? The way that we can tell whether something is in uniform motion or not on a speed time graph is really, really simple. On a speed time graph, something is in uniform motion if it makes a flat line. It's that simple. If that line changes at all, if it goes up like this or down like this, that means its speed is changing, okay? So when we're looking for something to be in uniform motion from a speed time graph, we're always looking for a horizontal line. If it's horizontal, then it's totally fine. If that line's going upwards, what that means is that its speed is increasing every second. Its speed is going up. So this thing's getting faster and faster and faster. If I had the opposite, let me try that again. Oh my goodness, everything's going wrong, guys. There we go. If I have the opposite, if I have a line going down, it means it's slowing down. Its speed is getting less and less and less as time goes on. But because we're doing uniform motion, we know that this thing is staying at a constant speed the entire time the graph is in, okay? Then it says, what does the y value of the graph tell you on a speed time graph? It tells us how fast it's going. This thing is staying at about 3.5 centimeters every second. So when I ask you, like, hey, how fast is this thing going at time 5 seconds? We do the same thing we did with the distance time graph. We look at 5 seconds. Oh, it's at 3.5 centimeters per second. So this thing is traveling 3.5 centimeters every single second, okay? Then it asks you to calculate the slope of the line. This is really easy here. I'm going to do it quickly with you guys. I'm just going to make give myself a bit of space here to work with, okay? So what I'm going to do is pick any 2 points on this line. I don't care which 2 points. I'm going to do this guy and this guy, okay? This one here is the coordinates are 5 and 3.5. Oh, geez. This one here, the points are 1 and 3.5, okay? Slope is a universal calculation, which means we calculate it exactly the same way in this case as we did in the last cases. We're going to go y2 minus y1 over x2 minus x1, okay? My y2 value is 3.5. My y1 value is also 3.5. My x2 value is 5. Oh, sorry, and I should say this is meters per second, or I think it's centimeters per second in yours. This is seconds, and this is 1 second, okay? So what I get when I do this is 0 meters per second every 4 seconds, okay? When you divide that, you just get 0, but your unit here is a little bit weird. Your unit here is meters per second, which is odd. It's a weird looking unit. In fact, we simplify it because saying per second is a little bit weird. We actually simplify that down to meters per second squared. Okay? And it turns out that what that is telling us is the object's acceleration. We'll talk about acceleration in a few weeks, but the idea of acceleration is how quickly its speed is changing. So when you think about that, again, it's meters per second. You can think of it like how many meters or how much the meters per second is changing every second. So if I had an acceleration of 5 meters per second squared, or 5 meters per second, what that means is every second, my speed goes up by another 5 meters per second. So if I started at 10 meters per second, after 1 second, I'd be going 15 meters per second, and then 20 meters per second. That's the idea of acceleration. Don't stress about it if you're not totally sure what that is now, but just know that the slope of a speed time graph tells us the acceleration. Okay, and one last point I wanted to make that I almost forgot about is remember on a distance time graph, we can tell how fast something's going by looking at how steep it is. Like this is going faster than this, as an example. Okay, on a speed time graph, we can tell if something is moving faster or slower than something else based on how high up the line is. So as an example here, let's draw a quick line. Okay, this blue line here is going slower than my yellow line, because it's got a smaller speed. This one's going like 1.7 meters per second, whereas this one's 3.5. If I have a line that's higher up, like this one here, what that means is that red line is going faster than my yellow line because it's higher. It's got a speed of 4.3 or 4.4, okay? So the way we tell if something is moving faster or slower on a speed time graph, it's just how high up the line is on the y-axis, right? So just to summarize now, all right, last slide today. Just want to quickly go through a summary of what we've talked about, okay? On a distance time graph, and you do need to double check which type of graph you're looking at, so always look at the y-axis. We know that the object is in uniform motion if it has a straight line, okay? So if I showed you the graph right now, as of the second, you should be able to tell me whether it's traveling, in uniform motion or not. Wow, I really couldn't think of that word. Okay, so just look for the straight line. Then we should know that the steeper the line is, the faster it's moving. Okay, the y value on a distance time graph tells me how far it's gone at that particular time. The slope tells us how fast it's gone. All right, and you should be able to now, if I gave you a graph, you should be able to tell me how fast it's going and tell me how far it's going at any particular point. On a speed time graph, we know that an object's in uniform motion if it's a horizontal line. All right, so again, you have to double check. If I give you a graph and say, is this uniform motion or not? Double check to see if it's a speed time or a distance time graph. On a speed time graph, we're looking for the line to be perfectly horizontal. The y value tells us how fast the object is moving, and if we calculate the slope, it's telling us the acceleration. I'm not going to worry so much about this today, but in a couple weeks when we do acceleration, you should be able to now tell me the acceleration from the graph.